Hello, everyone, and welcome to the Circuit Breaker Scroll Workshop, ZK Speedrun, 3 DSLs in 15 minutes, Noir, Circom, and Socrates. Joining us today is Ahmed Castro, who will be taking us through this session. And with that, I'll pass over to Ahmed to get the session started.
Thank you, Rory. Yes, we're going to cover different DSLs, which are the language needed to build circuits. So if you want to follow it with me, you can scan this QR code that will direct you to this page. And yeah, basically, we're going to go one by one, and I will just show the same process for each one, which you as a developer, maybe you're a Solidity developer that want to get into ZK. So what you need to do is first create the circuit, then generate a proof, then generate a Solidity verifier, and then you can verify that from a smart contract, and you can add some custom logic so you can connect it with your DAO or with your ERC20 tokens, or yeah, everything that we as a Solidity developer we are used to. Yeah, and also last workshop that we did with it global, which should be also on the, if you're watching on YouTube, it should be like in this like it global YouTube channel. I think it was really good. The circuit breaker attendees, like all of you guys, were asking some really good questions. So yeah, if you have any more questions about this, we can take a look at the end. So yeah, let's get started with Socrates. Socrates, it's I'm going to put it here. I'm going to open a terminal. So Socrates is okay. Here you go. So let's start with Socrates, which I think it has a really good developer experience. Here I already installed it, so you can first run this command, and then just put your username here if you want to load it into your environment variables. So here, I'm using Socrates 088. This is the installation part. So let's start by creating a proof. So let's create a circuit. And last time we mentioned that circuits are like the syntax for creating a circuit. It's very similar to a programming language, but the difference is that you write assertions instead of like you can compute stuff, you can create variables, loops, if statements, but the difference is that you make assertions, and only if all the assertions are like satisfied, are complete, you will be able to generate a proof. So here what I did is I have a circuit that has A and B as input. We're going to do very simple circuits for the sake of the example, but I think all of the example are going to exemplify like and get you in the right mindset to what you need to do in order to write any type of circuits. So this circuit is about two variables, A and B, and you're proving that A times A equals B. But A is a private variable. So you have two numbers and you only reveal one number and the other one is private. And in this case, we're like revealing only B. B is your public variable and A is your private variable. And we're going to generate a proof by passing these two parameters. A is 3 and B is 9 because 3 times 3 equals 9. So we run these commands, and now the proof was reading into the JSON file. You can grab from here, from the QR, the link to this here, to this to this page. I will be right back. Yes, can you
Okay,
hear me?
cool. Yeah, I can hear you now. Yeah.
Nice. Okay, yeah, I
Okay,
switched
cool.
my internet connection. Hope it's good now. Okay, let's continue then. So, okay, so basically I generated, so first I'm proving that 3 times 3 equals 9, but I'm going to keep 3 private and 9 public. And in order to prove it, I pass the 3 and the 9 as inputs, and what I get back is the proof, which is this one. So the next step is to verify the proof. So we're going to verify it on a Solidity smart contract. So I run this command and I get the Solidity verifier. Once I have the Solidity verifier, we can deploy this contract. And I'm going to deploy it on Scroll testnet, but it should work on also on Ethereum or on all EVM chains that supports all the precompiles needed for this to work, which are all the like layer ones, all the optimistic layer twos, and many. Just be aware that many ZK EVM don't support this yet, and Scroll does, but with a caveat that you have to restrict the amount of easy pairings that you do. So what you need to do as a developer, what you need to know is that this is very hard for ZK EVMs to support. Like the ZK EVMs will continue to like improve this in the future for sure, but now you have to know about the limitations about it. But yeah, we're going to do this on Scroll, which is working fine. And yeah, let's do that now. So first, I am going to have 2 contracts. One is going to be the verifier contract, which is the one that was generated by the DSL, which in this case is Socrates. So I compile it. There's some warnings, but yeah, don't have to worry about it. So now I deploy the verifier contract. And then I'm going to, this verifier contract is going to expose a verifier function. And that verifying function is going to be called from another smart contract. So let's take a look. So this is the verify function from the from my A times A equals B circuit. So this is the verifier contract. And what I'm going to do now is to deploy a second contract that's going to use this verify function. Let's take a look at this. So this second contract, we're going to call it like custom logic contract. So the custom logic contract is going to do 2 things. First, it's going to verify the proof. We're going to send a proof as parameter, and also we're going to send an input. And by the way, something that I miss here is that the proof has to be true. This is specifically for Socrates. This is the way like the Socrates smart contracts work. Incorrect proof. You can put a message here. So we're going to verify the transaction by sending the proof, and you have to get a valid proof to continue the execution. And what is the next execution? You can do whatever you want. For example, if you're doing like, I don't know, private transactions on ERC20 tokens, then you send the transfer here. If you're doing a DAO with a voting app here, you vote for the proposal. If you are doing social media, like anonymous social media, here you create the post. And here is the part, like here you can put whatever you're already used to doing on Solidity. So yeah, this is our contract, and let's try it out. So I'm going to compile it, going to launch it to deploy it, and as a parameter we're going to pass the verifier address that was generated from Socrates. So we're going to deploy this, and as you can see, we need to, in order to call the send proof function, we're going to need 2 things. One is the proof, and 2 is the public inputs. So you can find those here on the proof. So the proof is this one. This A, B, C thing is the proof. And the public inputs is this. You remember that we're doing that we're doing like A times A equals B circuit, and B is the public input. So we are not revealing A. And in this case, we are just passing B as parameter. Do you remember that we did 3 times 3 equals 9? So we're going to only pass 9 as parameter because that's the public input. So yeah, this is in a format that Remix won't like that much. So I'm just going to quickly put this in a format that it will like, the proof. So yeah, I think that should be it. And also I'm going to pass this as a parameter 2, which is basically also passing as an array of 1. And this should do it. There you go. And in this example, I'm just doing one thing with the custom logic. I'm just storing the public input, because the public input is what will allow you to play around with your ZK logic. And as you can see now, the public input was stored. And you can fake it. You can put just whatever number here because it's going to revert, right? So yeah, that's the cool thing about ZK. Okay, so this is Socrates. Okay, this is a speedrun, so we're going to go to the next one. If you have any question about Socrates, and if I can answer, like we can do that like at the end, as I mentioned before. Let's go with Noir now. We're going to do a very similar thing with Noir. We're going to go to the same process. We're going to get a circuit. We're going to generate a proof, and we're going to verify it. So let's do it. And okay, so I already have installed Nargo, which is the Noir command. I have version 22, which is the latest one. And here this is how you can install it on Linux, on Mac, and both Apple Silicon and Intel. And so let's create the hello world that Noir offers. And now we are going to pass you remember that we passed the 3 and the 9 in the command line for Socrates. In Noir, we pass it on this TOML file. So we're going to pass 1 and 2, and this is going to be run on this circuit that basically proves that X and Y are different. You pass two numbers parameter, X and Y, and you're proving that they're different, but you are only revealing Y. So X is private. So yeah, you're going to pass the parameters, you're only revealing one, but you can know for sure that the private parameter is another one, it's a different one. So now we're going to generate the proof, just like we did before. And our proof is going to be in the proof directory. This is a very long proof. Here you go. And now we're going to verify the proof, again, by generating a Solidity smart contract. Here you go. Here it is. And we're going to, the same as we did before, we're going to deploy this smart contract on chain. Remove this. Okay, this is the ultra verifier contract, which I think is a very funny and silly name because it's using the underlying technology of Plonk, about the version ultra Plonk. And they always keep putting these numbers like turbo Plonk, ultra Plonk. I don't know what's next. Okay, so we have the verifier here. It also has a verify function that we're going to call from a contract that I'm also prepared for today with custom logic. And in this case, we're going to do exactly the same. We're going to verify the contract. In this case, we don't need to put this one as required. This is the way that the Noir verifier contract is done. You just need to put this here to verify the proof that you pass as parameter. And you can see that we're passing the parameters in the same format. First the proof, and then the public inputs. And finally, you can add just custom logic, which we're going to do the same. You're just going to store the Y, the second parameter, the public one. Okay, so now the same as we did before, we have to specify on the constructor which verifier address we're working on, and we deploy it, and then we will have to pass the proof, right? And we have to pass it in a very similar way that we did before. So first we pass the proof and also the public inputs. So the proof is here, this super huge number. So just one recommendation for it to be compatible with Remix, you have to put the 0x at the beginning, and that's it. And then the public inputs, you can find them on the verifier.toml file that was generated for you. This is the only public input. So we are going to pass it in this format, like a string on an array. Okay. And we pass it on an array because usually you will want to pass many public inputs. That will help you to do the logic on 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 chain, like on your smart contract. So right now, the public input is 0, but when it gets confirmed, it's just going to become 2 on this case. Okay, here you go. The confirmation is confirmed, and we store the number 2. Okay, so that's for Noir, and now let's go with Circom, which again is going to be something very similar. Let me see if I have installed correctly Circom here. Circom. Yes, it looks like some install. So I'm not going to install, but I already have it. Let me just check if I have Snark.js also installed. Yeah, looks like it's installed. Okay, so if you want to install it yourself, you will need just run these commands, and sorry, that will get installed for you. So here, this is the Circum syntax, and we're going to do this circuit that is actually going to do some computation, which I think is super cool. Going to check for some computation, which we're going to check that the input A is going to be multiplied by the input B, and it's going to output on C. So yeah, we're going to check that A times B equals C. And yeah, so the only public input, which is the output, it's going to be C. So we're going to also create these files. So you remember that this is a bit similar to Noir, that we put the inputs on a TOML file. You were putting it on a JSON file, and then we're going to run all of this, which is going to, oops, I need to save this. Okay, we're going to run all of this, which is going to take a while because it's doing just you would have to be prompted just a couple of times to put some entropy because we're doing the power of tau, and you know that we're using the KCG ceremony for Core 16. So basically, it means that maybe some of you may participated on the KCG ceremony by the Ethereum Foundation, where everyone can contribute to the randomness, and the more people that contribute, the more safe get the protocol. So yeah, we're just going to do a couple of contributions here with just some random stuff, just to get it set up. And it's worth to mention that if you want to go, if you're using use some DSLs that use trusted setups like this one, and once you go live, you may want to do it like in a very safe way, or you may use some other snarks that don't use this initial setup, and in that case you won't need to do this step. So yeah, it will depend on what DSL you're using, and each one has some pros and cons. So before launching, I would recommend you just go into the forums from that language, from the DSL, and just ask like what recommendations are there. So far, as you can see, the three of them have very similar characteristics, and the language may look different. You may have your favorite yourself, and but in general, they're all the same. They have inputs, and they have public and private inputs, and you do assertions, you do checks, and then if everything is correct, then you will return a proof, and yeah, that proof can be generated. It can be verified in multiple ways. It can even be verified like off-chain. You don't have to do blockchain stuff in order to do ZK. But of course, doing like verifying on Ethereum is something very unique because it allows you to have something that can be public and verified by multiple people. So yeah, Ethereum is giving us this property that which is super cool. Okay, so here the inputs of the proof. So we basically pass during all of these. Okay, we are computing that here, the input, that 3 times 11 equals 33. So 33 is going to be our public input, which is exactly here. This is the public input. So basically, this is the proof. This is the proof. And this is the public input. It's like 21, but it's 21 on hexadecimal, which is 33 on decimal. You can also see the proof here. This is the proof, and yeah, this is the proof, and this is where is the public input. I can find it here. Well, anyways, this is the public input, and it is in the format that you will already expect it from Solidity. So again, let's do the same process again of generating the verifier. Here you go. And the verifier is here. Again, we can go and put it on Remix. We can deploy it. And also we can now create a custom logic circuit, which is very similar to what we already did. We pass the verifier as parameter. And in this case, the inputs are already formatted here, so it's going to be very easy to pass them. And of course, you on your web app, as we mentioned in the previous circuit breaker workshop, you will usually want to build this on a web app. And when you do it, well, you will have like each Socrates, Circom, and Noir have some JavaScript way of doing everything, JavaScript way of passing the parameters, and JavaScript way of generating the proof. You will usually want to do it there unless you're doing some backend stuff, some proving on a backend, not like specifically a privacy app. But privacy apps are like I think something that very new, very unique, something that was not possible before and now was by using our Ethereum accounts, which I think is super cool. And it's something that you can use on layer 2s to save gas. So I think that it's a good, like doing privacy app on layer 2s is something that we as developers, there's a lot of opportunities here because there's something very new and a lot of room for creativity for us to think about new stuff. So yes, you can see here, I pass the parameters and I verify the proof. Now it's on there, just very simple custom logic. But yeah, this is my overview of the three of them. Each one has different characteristics. If I can summarize what I think personally about each of them, I think Circom is like the one that has more adoption, has more community, and yeah, I think it's super cool. And I think that Noir, the team is working super actively on it. I like a lot what the team is building, and also I think they're very focused on developer experience. And also Noir, on top of being the language for creating a circuit for EVM language, there is also going to serve to create circuits in a non-EVM language that's going to be the ASIC layer 2, which I also think is super cool. But this means that it is a project that is being worked on a lot. So it's very active, has a very active development. So I think that's super cool. And about Socrates, I think the interface is really good and it's very easy to pick up. The documentation is really, really good. And yeah, probably I would recommend this as your first experience with CK, either Socrates or Noir. I think Circom is more complex. Yeah, but yeah, for developer experience, I think it's very easy. But I think that that there is more activity on Circom and on Noir, but yeah, each one has some features over the other. So when you want to like actually build a project using either of these, you will have to check if it has everything that you need for your specific app. So yeah, this is my speedrun. Probably it took me more than 15 minutes that I was planned to, but yeah, happy that you guys tagged along. So yeah, let me know if you have uh, any questions.
Yeah, there was one towards at the top saying I wish you would go back to the ways one can use the verifier.sol. They thought that you rushed that a little, but maybe because it was in 15 minutes.
Yeah, like about generating the Solidity file. Yeah, so the thing that you need to understand is that there are two contracts. One contract is generated for you, and the other contract is like your logic, like what you usually write in Solidity. So let's pick, for example, I think this one is a good example. So with this command, you generate a contract and you deploy it, and yeah, it's going to be sitting there, and yeah, it just has a function that you pass the proof. It returns true or false if it's, or it will revert if the proof is false. If not, it will, your program will continue. That's one contract. You don't need to write it; it's going to be generated for you. And yeah, it's going to have a lot of numbers that you don't need to understand. The only thing that you need to know is that it will have a verify function. And the verify function is going to be called by the other contract that that's where you will be coding. And what will you be coding here? So you will have basically on one side you will need to verify. So we have a verifier call to your other contract. So the previous contract that was auto-generated, you're going to call the verify function from that contract, and if it passes the proof, because you send the proof, and if it's not correct, it's going to revert. So if you pass a correct proof, then you can add your custom logic. And what things can you do on your custom logic? So you have a couple of like tools that you can build here. So one part is that you have the public inputs. So when we pass stuff to the circuits, you have the public and the private inputs. So the private, no one can know about it, especially your smart contract. It doesn't know about it. Why? Because it's private and everything on your smart contract is public, right? So the private stuff is going to stay off chain. It's going to stay on the circuit. No one will be able to see it. But the public stuff is going to be here, and uh, you can play around with the public information on your uh, here on Solidity. For example, if you're doing a voting app, the you can play around with stuff such as you can keep the voter anonymous as a private input, and you can keep the vote public as a public input. So the public input is going to you can play around with it. You can do your Solidity stuff with it. You can do some computation, whatever you want. And yeah, on the other hand, for example, you can have for example, a DeFi staking protocol, for example, that if you want to stake or on stake, for example, when you're on staking from a public perspective, you will only be able to see the public params is the amount that you are on staking and where it's going to be sent. But the private input is the original owner. You won't see it because that's the anonymous part. So it will depend on your app. So you have some privacy stuff that will stay on the circuit, and all the public stuff you can play around here in Solidity. So that's like your custom logic. So that's what you will be able to do here. So yeah, so two things that you here. First, verify, which is called the other contract, and second, just whatever you want to do, your custom logic. Yeah.
Nice. And another question was, I would like to know if you can touch on converting arbitrary statements to math, what is fundamental to creating circuits that would create the proofs.
Yeah, I am not the right person for that, but I'm not very familiar with all the math stuff. But there is the CK, the best resource that I found so far, which is like a good like middle point for all the math and also a little bit of programming stuff. Is the CK MOOC on on by Berkeley on YouTube. I think this will be my full recommendation here. Yeah, I think it has both, and it go like very low level. It will go very low level on everything that they need to touch on. So yeah, you can find this on. This was done by the Berkeley University. Yeah, this will be like my recommendation. This is the most up to date. And yeah, but yeah, I'm not the person for the math stuff. Yeah.
Let's see. And then should we check out the .ptau or .r1cs files to get, or is it better to ignore them?
Oh, the this one, like this. So as a developer, you don't need to touch on these files. Yeah. Other the PTAO, you don't need. Yeah, you can just like ignore it, and you will need them to uh, to to generate the proofs and to verify them, and also to make the verifier contract. But yeah, as a developer, you don't need to touch them. You just need to open up your ceremony so many people can contribute to it and to make it more safe. But after that, you don't need to touch it anymore.
And I think you may have mentioned this, but which HDL among these is most user-friendly for beginners?
Yeah, I think either Socrates or Noir. That would be my two recommendations. But just take into consideration that Circom has more community, has a bigger community, and also has a bigger um, like more projects have launched using Circom. So there are more like use cases and example projects. Just take it into consideration. But as you can see here, like it has these signals and these like this is the way of checking constraints. And yeah, I think for developers, if you're coming from maybe you're a Web2 developer or you're a Solidity developer, I would recommend either Noir or Socrates. And also the Noir guys have been like putting a lot of effort lately on the documentation. So yeah, probably Noir. Yeah, I would say Noir. It will depend on the project.
Okay. In the Noir example, upon submitting the proof in customlogic.sol, the public number was updated from 0 to 2. How does this prove that the numbers are not equal as was written in the Noir code?
Yeah, so we passed 1 and 2, right? First was the x was 1 and y was 2. So what we're proving here is that we passed a number that is not 2. So, but this particular example doesn't, it's not like practical, like just this is just an example, but let's put this like into a practical context, like an example with something practical, is that okay, you can, for example, if like I mentioned before, like if X is your, for example, you have a list of voters and like an array. You can imagine an array of voters, which is X your private input, and Y is your public input, which is the vote, like for or against. Maybe two means against, one mean for. So when you pass the when you go to the contract, it is relevant at this point because you already know that only if you are part of the list you will be able to generate a proof. So that's where like private keys and public keys come into play because you can only prove that you are you are part of this list only if you have a private list, for example. And usually this is done by using hashing. So you can think about only if you have the key, you can unlock the private part, but the public part is just public. So you can't generate a proof if you don't have the key. So, but the key is going to remain private. So that's the important part. And so you can safely go and submit this on blockchain with a proof that you were only be able to do it if you have the key. But if you have it, you won't expose it. That's the cool part. So and also you won't know probably if it was list, for example, you won't be able to know which one were you. So yeah, different things that you can play around with here. This example, as I mentioned, is not like really. It's very straightforward. It's just it doesn't it's not practical just to say like okay X and Y are different because you could have picked like one or three or four or five or six. You don't know which one. The only thing that you know is that you didn't pick two. And the thing is that you can, for this example, you can generate an infinite amount of proofs, uh, or you can generate like the a different proof with the same number for one and two. You can generate the same number two times. So as a developer, you also have to think in ways on how to restrict the proof generation. Maybe you can uh, you can um, you can think of ways of how to make people not to do the same thing two times, like to double spend. And here you will also need to be using like nullifiers and stuff. I'm going talking about other stuff, but in general, you as a developer, um, what you will care about is the public inputs and how to not double spend and the nullifier. So yeah, in this example, the just passing one and two doesn't say too much, but the power of ZK and the thing that we were not able to do before is that this is going to be obscured. No one will be able to know what was it. I don't know if that answered the question.
Okay, and then last question, what of Halo 2?
Hmm. Yeah, really good question. I thought about adding Halo 2 here, but yeah, it will definitely not be a speedrun at all. Yeah, Halo 2. Actually, Halo 2 is not a DSL, but it serves the same purpose that the three of them. So how are they similar? How Halo 2 is similar to Noir, Circom, and Socrates. So on Halo 2, can you write circuits? Yes, you can write circuits. Can you generate proof? Yes. Can you verify them? Yes. Can you generate a Solidity smart contract that is able to verify the proof? Yes, you can do that too. And how is it different? How is it different than all of the three of these? And as you may have known, scroll is reading on Halo 2 because the privacy exploration from the PSE, privacy and scale exploration repository from the ZK is reading on Halo 2. And why did they decide to do it on Halo 2 and not on these others? It's because Halo 2 is more flexible. It allows you to go like one step deeper and fine tune like everything that like more like you can go like one step behind into the into the more a little bit more cryptographic part, and you can think about it as a you can write code in C, in C++, for example, but you can write the same code in C or even in assembly. It's going one step lower, and yeah, so Halo 2 allows you to go one step lower and just do more like specific stuff that you won't be able to do in neither of this language. But the problem is that it's very complex, and you just need to fine tune because you have all these different possibilities. You have to understand a lot of concepts first, and it's also not a DSL because, as you can see, the DSL are a dynamic specific language. So it's a language that that serves only one purpose. So Socrates, Noir, and Circom, it serves only one purpose: is making CK proofs. But Halo 2 is not a DSL, it's a library, it's a Rust library. So you write your Rust program and you import the Halo 2 library, and you can start writing your circuits that way. And as you may have, as you may suspect at this point, the syntax is very, 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 very hard. Yeah, it's very hard, but it's also very cool, and you can do a lot of cool things, and that's why it's the preferred language for the CKVM. That's the language the library is not a language, right? It's a library. That was a library that was picked because it gives you a lot of flexibility, and it expands the things that you can do. But unfortunately, and the reason why I didn't add it to this like speedrun is that you just don't have this like Halo 2 export verified. You just don't have it. You have to write the Solidity itself. Maybe in the future you will have like a command that will allow you to do it, but it's not there yet. It's not there yet. And also it's not the main reason of Halo 2 to exist, because Halo 2 was developed, I think, by the Zcash protocol, and now it's used by Scroll and other projects. But yeah, the thing is that the objective is just going very deep and doing this low level stuff. The objective, not the developer experience. But in the case of Socrates and Aztec and Circum, yes, the objective is the Solidity verified. That's why it is the developer experience. That's why you can have Solidity verifiers and all that stuff. Yeah, but yeah, really good question, because Halo 2 like is part of this group of tools that allow you to do the exact same thing.
Nice, awesome. Well, cheers. We're a bit over time, but yeah, thanks again, Ahmed, for another great workshop presentation, and thank you all, everybody else, for asking these really thoughtful, insightful questions. As a reminder, hacking has begun, so you can begin hacking. Yeah, we got one more workshop this afternoon, and then another team formation session. So awesome! Everybody has a great rest of your Friday, and have a great weekend.
Yeah, thank you, Rory. Thank everyone for all the for participating and doing all these great questions. Yeah, and yeah, happy hacking. And yeah, can't wait to see what you build on Circuit Breaker.
Awesome. Cheers. Have a good one, everybody.
Bye.
Bye.